Hello. Hello, everyone. It's a great pleasure for me to welcome you to our KIOS Distinguished Lecture Series. That's an opportunity for us to hear from some of the work they're now the researchers about the challenges they are working on. Today, our distinguished lecturer is Christos Cassandras, and it's a great pleasure for me to introduce him. He's a great friend and a great friend of KIOS as well. I think he has been here a few times in the past. I will go over his bio before I let him take the floor and tell what he's working on. So Christos is a distinguished professor of engineering at Boston University. He is head of the Division of Systems Engineering, professor of electrical and computer engineering, co-founder of the Boston University Center for Information and System Engineering, SASE, where I used to work for a couple of years. He received a bachelor's degree from Yale University, Stanford, a master's degree from Stanford, and a PhD from Harvard Universities. He briefly worked in the industry before he joined University of Massachusetts at Amherst, where he won all the ranks and became a professor. And after he went to Boston University, he has published more than 500 refereed papers in the areas that he's working on, which I forgot to. He specializes in the areas of discrete event and hybrid systems, cooperative control, stochastic optimization, and computer simulation, with applications to computer and sensor networks, manufacturing systems, and transportation systems. He has also written 8 books. Some of them have received awards. He has guest edited several technical journal issues and serves as a journal edit in several journal editorial boards. In addition to his academic activities, he has worked extensively with industrial organization on various systems integration projects and the development of decision support software. He has most recently collaborated with MathWorks in the development of the discrete events and hybrid system simulator SimEvents. Christos is the editor-in-chief, was the editor-in-chief in the transactions of automatic control, and he served as an editor on the technical notes and correspondence. He is currently the editor of Automatica. He has served as the president of IEEE Control System Society and also served as the vice president for publications on the board of governors of Control System Society. He has chaired several conferences, and he has been a plenary speaker at numerous international conferences, including the American Control Conference, the IEEE Conference on Decision and Control, and the IFAC World Congress, and has also been an IEEE Distinguished Lecturer. He's a recipient of several awards, including the 2011 IEEE Control System Technology Award, the Distinguished Member Award of the IEEE Control System Society in 2006, and the 1999 Harold Chestnut Prize, the IFAC Best Control Engineering Textbook for discrete event systems, modeling, and performance analysis. He has also received some awards from IBM and IEEE Smart Planet Challenge competitions for the smart parking and street bump system detection algorithms. And he has received the Distinguished Scholar Award at Boston University and several honorary professorships, the Lilly Fellowship, the Kern Fellowship. He's a member of the Phi Beta Kappa, Tau Beta Pi, and also a fellow of IEEE and fellow of IFAC, and holds chair position at Tsinghua University. And without further ado, I present Christos.
Well, thank you. I feel like my life just flashed through my eyes. I hope that doesn't mean that I'm going to die now. Okay, so thank you very much for the introduction. This is a talk on multi-agent systems and the concept of autonomy, in particular, safe autonomy. And my main motivation for the theoretical part of this work is making autonomous vehicles a reality, where it's not enough to be able to just control the vehicles, you have to guarantee safety. I don't want to buy an autonomous vehicle and not guarantee that it can drive safely. Oops. There we go. So on the theoretical side, to give you the motivation of this work, consider optimal control techniques, which are extremely effective when you can solve the optimal control problem, and it's very general. But the problem is that it's very hard to obtain a closed form solution, especially when there's lots of constraints which become active simultaneously. It's very time consuming to compute. The models typically have to be limited to fairly simple ones to be able to get analytical solutions. And it's not very robust to disturbance. In other words, every time a parameter changes, you have to resolve an already difficult problem. Now, a lot of people develop ad hoc controllers, which are much easier to obtain. They can handle nonlinearities, constraints, noise, and so on, but there's no guarantee of optimality anymore, and you can't even measure the extent of suboptimality. And there are no constraint guarantees, which is really the main motivation for the work that I want to do. And so I feel that there's a need to bridge the gap between optimal control theory and real-time ad hoc controllers so as to achieve sort of this joint optimality with safety guarantees. On the more practical side, my motivation comes from what we call the Internet of Cars, which is the emergence of connected autonomous vehicles. I think we're all pretty much familiar with that. It is an advancement which hopefully will allow us to move from the selfish optimality of the individual driver behavior, as we know drivers behave today, to social optimality, if you can coordinate and have the vehicles cooperate in what we call the Internet of Cars. And the importance of cooperations came very clear to me when, not too long ago, I think it was last summer, I was walking around the campus of Boston University, and I saw this car with a bumper sticker, which I have large here, and I thought I should take a picture of that because that's exactly what I was working on at the time, safety in merging of cars with guarantees. So that's another part of the motivation. Now, one question that I'm frequently asked is, when you guys develop all these nice algorithms to achieve cooperative control zone, how do you test them? And the answer is, of course, in simulation most of the time, but it is very important to test our results also in the real world. And the best place that I know of in the US is this facility, which is known as M-City. It's at the University of Michigan. And we're fortunate to have a project that lasted for about 5 years, ended a couple of years ago, where we had this autonomous vehicle. It's actually an Audi e-tron. And we were able to test a lot of our algorithms in the M-City setting. And I like this M-City setting because it allows me to focus on what we call the control zones, the conflict areas where there are opportunities for connected and autonomous vehicles to really shine. So you have intersections, you have merging, like in an on-ramp here, you have roundabouts in M-City, there's 2 or 3 of them if I remember correctly. Also intersections, which are both signalized and non-signalized. And also there's a stretch of a kind of like a highway, it's not very long, where you can test your lane changing maneuvers. So all of these, we call them control zones. And the goal is to coordinate and have the vehicles cooperate at all of these control zones to achieve desirable performance. And what do I mean by that? I mean 4 things. First, minimize travel time while you go through a control zone, like through a roundabout or an intersection. Secondly, minimize the energy, fuel consumption or electrical energy. Thirdly, preserve comfort, because we have observed that sometimes you can go way too fast, for example, around curves, which makes passengers quite uncomfortable. And perhaps most importantly, guarantee safety. The keyword here is guarantee safety. So as an example, if you take the merging problem, which is one of the easiest ones to handle in this context, you have a control zone where there's some entry points and some exit points, usually defined by the communication capabilities, the range that is involved. And you have an entry point and an exit point with corresponding times. We usually have fairly simple dynamics for our cabs in order to be able to get the analytical solutions. Of course, part of what I want to talk to you about is to get beyond that. You could have an additional state variable, which measures the jerk. This is for passenger comfort. And the goal is to achieve the objectives that I mentioned before by typically controlling acceleration, and in 2 dimensions also controlling the steering of the car, which I'll get to. So we can formulate a very nice optimal control problem of this form, and you can see the components of the objective, which involve the travel time, the energy, and the comfort. And these are also subject to the dynamics of the vehicles, constraints imposed on speed and acceleration, safety constraints, the most important ones. And the idea is that you can solve this problem given some initial time, an initial state, initial speed, initial position, initial speed, and also the position of the exit point for this control zone. So T sub I super n denotes the merging time, which has to be found optimally, as you can see. All right. So we can formulate problems like that for any control zone. We can also put multiple control zones network together and try to solve this difficult problems. Now, the challenges are, first of all, whenever you deal with an optimization problem, you don't even know if there's a feasible solution. So before I even try to solve a problem like that, are there simple ways to check for feasibility? Can I solve in real time at least the unconstrained problem? If I relax all my constraints, can I solve the unconstrained problem? Because if I can't do that, then I might as well go home. There's no hope to solve the constrained problem. Can we easily detect when constraints become active? Because if we can easily verify that some of the constraints are never active, then that helps. Of course, can we solve ultimately the fully constrained problem in real time? What if the constraint solution can be obtained, but not in real time? Is there some way in which we can find still methods to deal with the problem in real time? And finally, of course, go from the planning to the execution phase of an optimal trajectory that I may have been able to determine. And this is where I want to bring in fairly known and some more recent developments, which involve model predictive control barrier functions, which I'll talk a little bit about, and also, of course, reinforcement learning. How could I stand here and not mention the word learning to you? You think that I'm a dinosaur. Well, I know how to do learning. I just don't want to do it for stupid problems. I want to do it for learning actually can buy me something. All right, so a definitely inadequate kind of summary of what people have done over the years. Some of these problems have been dealt with a long time ago, including a very well-known piece of work in California that Praveen Varaya led in the early 90s, the so-called PATH project that was abandoned after a while because the technology wasn't there. Now it is. But you can see that most of these papers have been written in the last 20 years or so. All right, so let me get straight through the first of these control zone problems, the merging problem, which you can see depicted here, which is one of the easier ones to deal with, and show you that actually we can obtain a complete analytical solution of this problem without going into details. So this is what the basic merging problem looks like. You see that there's a merging point over here where we would like all of our vehicles to go through without colliding, obviously. There is a coordinator which is associated with that area. Sometimes this is done by the so-called roadside unit or RSU, but I want to emphasize that this does not do any control or optimization. It just simply records information and facilitates the passing of information among those connected autonomous vehicles. And by the way, notice that so far I'm assuming that all the vehicles are connected and automated, okay? Halfway through my talk, I'll say, all right, that's good. How do we get to the next step where we mix connected autonomous vehicles with human-driven vehicles? And I'll tell you a little bit about the work that we've done on that. Okay, so the key is that we want to go through this merging point safely. We, again, assume fairly simple dynamics for our calves, and notice that it's a one-dimensional model. I'll get into two-dimensional models later, so it controls the acceleration along a lane. And the key quantity that I want to focus on is this distance between a vehicle I and its physically preceding vehicle indexed by I sub p, because that defines a lot of the safety constraints. Specifically, we have this standard safety constraint that says that the distance between two vehicles must be greater than some fixed distance, but also something which depends on the speed, because the faster you go, the more difficult it is to decelerate and preserve safety. And this constant phi is what's referred to as the response time, which, depending on what country you live in, is between 1 and 2 seconds, typically taking up to 1.8 seconds. Notice that a similar constraint applies to the merging point, but it only needs to be satisfied when the vehicles get there at TIM. And TIM is part of the optimization problem. All right, so this is the standard problem formulation. It's similar to what the general form I showed you before is, except comfort has not been included here. And the reason is that if you get an optimal solution, it turns out that it's a comfortable solution. So these are all the constraints that we need to deal with. And notice that it's a decentralized optimization problem because I'm looking to optimize over an individual vehicle, decentralized in the sense that the target vehicle, sometimes called the ego vehicle, needs to exchange information with at most 2 vehicles. The vehicle ahead of it and the vehicle with which it will compete at the merging point, which has to be determined separately. All right, turns out that if you eliminate all of the constraints, it's a very easy optimal control problem to solve. And look how simple the form is of the solution for the acceleration, that's the control, and then the speed and the position of an optimal trajectory. There are 2 cases to consider. One, when the physically ahead of you vehicle is in the same lane as you, or not. But the solutions are pretty similar. So here I'm showing you what happens for the case where the 2 vehicles are in the same lane. And it turns out that the solution just comes down to determining this A, B, C, D constants, which are determined by this set of nonlinear equations. Never mind the details. We know how to solve nonlinear algebraic equations, so it's not too hard of a problem. Now, if constraints start kicking in, things get a little hairy. For example, in this trajectory, there's a segment which includes the activation of the rear end safety constraint. Those 2 vehicles got too close to each other, and they must preserve the safety constraint. So you need to solve a separate problem here. You need to determine when this becomes active and when it ceases to be active. And it turns out that you can again obtain a set of more complicated, but still doable analytical solutions for this problem. This is the bottom line that I want to simply leave you with. That we can always obtain a complete optimal solution, but when constraints become active, the computational cost increases. So the purely unconstrained solution takes a lot less than a second, milliseconds. But when a lot of constraints become active, this can get up to like 20 and 30 seconds. That's not real time, at least not to me. This is an example of how things can get complicated when you look at trajectories with constraints active. So the y-axis is the control, the acceleration. This is time. You can see that the first vehicle that enters has a very, very simple solution. It accelerates, but it reduces its acceleration until it reaches the merging point, at which point it reaches a constant speed. But the interesting thing is what happens when you have something like CAV3 here. All the colors indicate the different arcs on the optimal trajectory. And there's 1, 2, 3, 4, 5, 6, 7, if you count the colors. And I need to have different solutions for each of the 7 segments. Plus, I need to know exactly when the segments start and stop. So this is an illustration of how things can get pretty complicated. Which brings us to what do we do in this case? And how do we take what we've learned from this exercise of finding solutions analytically to the real world, where we want to solve these problems in real time. And this is where we'll talk a little bit about control barrier functions as the tool that allows us to make this transition. I've shown you this picture before. I just want to show it to you again by replacing what I call real-time control by various options. So this is one option. You can say, well, let's use model predictive control. I'm sure many of you are familiar with model predictive control. If you're not, it is one of the most popular practical methods that have migrated from sort of the academic part of control theory to the practical side. It's a receding horizon control approach, which works very well, but it is suboptimal for sure. Typically, you can only solve the linearized versions of your models. So there are linearization errors if you are working with nonlinear systems. The models are still pretty simple, and it's computationally expensive if you want to predict the future way ahead. Reinforcement learning is something that we've tried fairly recently that works well. Why? Because it's very general and typically model-free. Well, that's nice, but again, there's no guarantee of optimality. It is computationally expensive. You have to train your system and so on, and there's no constraint guarantees. So that's the big one. And that brings us to this notion of safe learning, which is a much broader topic that I know a lot of my colleagues in AI, machine learning, and so on are preoccupied with these days. The other option is using control barrier functions, which I will advocate, and then I will tell you how to bring all of these techniques together. Control barrier functions allow you to solve these optimal control problems very easily. They have this very important property, which is called forward invariance, which means that if you start safe, you stay safe. They can handle nonlinear dynamics and nonlinear constraints. They can handle much more complex objectives if you want to enrich your objectives. They're fairly robust to noise, but they are also suboptimal. But luckily, we have the tools to kind of quantify and control the level of suboptimality. And by their nature, they are possibly conservative and myopic. So this is the price to pay. Okay, now the Holy Grail is if we can combine all of these wonderful tools, control barrier functions, reinforcement learning, model predictive control. And this is something that we have been doing lately. And you can bring all of the nice advantages of each one of these techniques without the flaws of each technique. And by the way, the combination of these two, at least, using reinforcement learning with CDFs, allows you to do your training online with guaranteed safety. That's important because, as far as I know, a lot of people, when they train, for example, algorithms for autonomous vehicles in simulation, hopefully not in the real world, they allow for crashes and they learn from the crashes, trial and error. That's the way learning works. Well, incorporating control barrier functions in the training part of any learning algorithm allows us to learn while we remain safe, which allows us to do the training online. I hope to give you some example of that. So the idea here is that if you parameterize your model predictive controller and your CBF controller, you want to learn those parameters. In my opinion, this is a good use of learning. Learn the parameters of something that has been developed based on rigorous, intuitive, good techniques, and then just learn the parameters of those techniques. And in particular, in reinforcement learning, we can parameterize our controller and then learn the parameters. Okay, so here goes an overview, a 5-minute, everything you wanted to know about CBFs that we're afraid to ask, overview of CBFs. The whole idea of control barrier functions is to consider a control problem in which you want to stay within a bunch of safe sets, the intersection of all the safe sets. So you want to control your system to always remain in this area. Well, okay, maybe you can do that, but if you're a control guy, what you really want to do is develop a feedback control policy which does that, not do just open loop. So the idea is to learn or be provided all the information you have about your system and the constraints that you want to consider to define this safe region, and then determine a control which has this forward invariance problem, meaning that if you start safe, you stay safe. And this is what CBFs do. So how do they work? The starting point is a very nonlinear system. The only concession is that we want to be affine in control. That can be relaxed also, but most of the time for a lot of the electromechanical systems that we deal with, they satisfy this assumption. Other than that, this is very nonlinear. So there you go. I don't have to now limit myself to just second order vehicle models. The only, theoretically speaking, assumption that I need to make here is Lipschitz continuity, which is, I think, fairly easy to check. Now, control barrier functions are essentially constraints of this form. They give you functions of your state that you must always satisfy. For example, safety constraint distance between two vehicles. But notice that these are only given in terms of the state. What I really want to know is the control that will enforce those constraints. So the CBF method, what it does is it takes these constraints and it maps them into a different kind of constraint, which allows you to determine the control that guarantees each one of these constraints. These outputs of these maps have this general form. Now, this may look a little daunting, but actually it's very simple. So the first two terms take the original constraint that you have and determine its lead derivatives. If you don't know what a lead derivative is, here's the definition. All it is the partial derivative of a function v along the dynamics, along the f and the g. And the third term is what is known as a class K function. A class K function is essentially any monotonically increasing function that starts at 0. So this is really the barrier. And this is a simple inequality. So the idea is that every control, which you see in the middle term here, that satisfies this inequality implies this. So now I have a recipe that says, if you want these to be satisfied, just determine the U's that satisfy this inequality, which, as you can see, is easily determined. Trust me, these are just derivatives that you can compute. And then this, which you control, you can determine different kinds of class K functions that are convenient for you. So what I want to emphasize is the linearity in this inequality. So it's easy to solve. Just solve this inequality. And when you solve it, you have a set of feedback controls that guarantee the original constraint, and on top of it, they guarantee this forward invariance. There's a book that I've written and was published a year and a half ago, I think, with a former student of mine and a colleague, which provides all of the details, proofs, and lots of applications of control barrier functions. Now, sometimes your constraints that you want to enforce are not hard, but soft. I have an example here, which is a vehicle that wants to stay as close as possible to some reference speed, so you want to minimize the quadratic distance from it. And in that case, there's also what we call control diagonal functions, as opposed to control barrier functions. And they play the same role, but in this case, you want, rather than enforce an inequality which has a 0 on the right-hand side, it has a small number that you would like to minimize. So what do you do after you build this sort of edifice of control barrier functions? You formulate an optimization problem in which you would like to minimize the deviation of your control from 0. So basically keep the control as small as possible. So a good controller. And you also want to minimize this delta, which is the relaxation constant for the soft constraints. And this is all subject to very general, as you can see, nonlinear dynamics, a bunch of CBF constraints, a bunch of CLF constraints, a bunch of control constraints. And the only thing that I want to emphasize is that these are your hard constraints and these are your soft constraints. So sometimes you may not even have these, you may not have these. And this is another optimal control problem, but it's much simpler because these are all linear in control. In fact, practically what you do is you discretize time and you solve over each time step, which I indicate here, a bunch of quadratic programs. Why are they quadratic programs? Because you choose your objective function to be quadratic, and all of these constraints are linear in the control. The only caveat is that you have, like any discretization method, you have to pick the discretization time slot, which may not be trivial, because you notice that in this discretization, you force the control to stay constant over each one of these points in time. But my forward invariance property is not guaranteed over discrete time, but over continuous time. So if I don't pick my discretization well, then what's going to happen is I may become infeasible in some of these time steps. So this is a problem. How do you overcome this problem? Event-driven techniques. So what you do is, instead of picking arbitrarily delta t's for your time discretization, instead you define events and you trigger the next activation of this quadratic program based on appropriate events. As a side benefit, for those of you interested in security, you get a freebie, which is increased unpredictability, because no longer is there a fixed time step, but it's unpredictable. I don't even know as a controller when the next iteration of this QP will be, because it's just an event which happens, subject to noise or whatever. So this is a benefit of event-driven methods. There's a recent paper that describes how we do that. Okay, now there's a lot of issues once you get into control barrier functions, and I'll just list some of them and just mention how, just give you a hint of how you resolve at least one of them. The first and obvious one is this. I told you that you solve this inequality for U in order to determine the feedback control that tells you how to satisfy the underlying B greater than or equal to 0 constraint that you want to satisfy. Okay, but it's possible that this derivative is equal to 0. If this derivative is equal to 0, you can no longer solve for the control. So I've got a problem. Another problem is, and I sort of mentioned that, is that once you discretize, or even with an event-driven method, you segment the timeline onto intervals over which you solve a QP. Sometimes these QP problems may become infeasible in themselves, in which case you return. Now, this is perhaps the most interesting one, conservativeness. Effectively, what this mapping that I described from the original constraint B of x greater than or equal to 0 to the CBF inequality, that particular mapping creates a sufficient condition for my original constraint to be satisfied. A sufficient condition can be conservative. So what I'm doing is I've bought a lot of safety guarantees by being conservative. In the limit, that's pretty stupid. Of course, I can get the entire transportation system to work very effectively and safely by forcing all the cars to drive at 5 miles an hour. I don't think we want to do that. So we have to confront this trade-off between conservativeness and performance, and we know how to do it. What if the environment is time variable? Certainly, in the context of autonomous vehicles, traffic systems change all the time. So this is what led us to develop what we call adaptive control barrier functions to deal with this problem. What if the dynamics are unknown? You could argue that I may know my own dynamics as an autonomous vehicle, but what about the other guys that I'm supposed to communicate with and interact with? I may not know the dynamics. So all of these we are aware of, and many of the solutions, again, can be found in this book, and many of them we're still working. Okay. All right, so I'll just give you a little bit of a sense of how you at least overcome this pretty fundamental problem. And the trick is to simply keep taking derivatives, not just one, but multiple, until the control shows up. And when you do that, basically you create, instead of a single safety constraint here, you create a bunch of safety constraints, including the derivatives of the constraint that you started out with, and you end up with an inequality which is a little bit more complicated than what I had before. Notice that it's still linear under control. It involves a few derivatives. So there's this notion of the relative degree of a function, which is the number of derivatives you need until the U shows up, basically. And again, you end up with an inequality of this type. So we know how to deal with that problem. Now, I advocated bridging the gap between optimal control and the real world. The way we formally do that is through what we call the optimal control with control barrier functions approach. I'll give you just a high-level picture of how that works. So consider this optimal control problem where you have to get a trajectory, this red trajectory, which does not violate a constraint, which is denoted here by this unsafe region, which the optimal control system in general will. So the idea is to go here and try to find the blue trajectory, which is as close as possible to the unconstrained red trajectory, but guarantees to not violate any of the safety constraints. So to do that, what you do is you solve the unconstrained problem. You might get some feedback if you want to do it in real time to create a reference control. In the simplest possible case, that's just the unconstrained problem. And then you solve a new optimal control problem where all of your original constraints, the hard constraints and the soft constraints, are replaced by these CBF-based functions. That's the whole idea. And as I said, in the simplest possible case where you don't have feedback, you just use the unconstrained solution as your reference, and you try to essentially find this blue path, which is as close as possible to the red path. I'm going to skip the details, but I think you get the high-level idea of how this works. Now, let me bring in learning. So what we recently did is we created this sort of architecture, which includes sort of like, if you like, 2 time scales. A time scale, which is based on a standard actor-critic update. Those of you who are familiar with that, if you're not, that's okay. And then this is the important inner loop in which you do your training and your real-time execution of the trajectory. And I remind you that in our case, the training can be done online with safety guarantees. The important thing is that the controller that we have now contains a lot of parameters. Where do these parameters come from? Some of them come from the control barrier function inequalities here or here, and they are the parameters that describe those class K functions, basically how you choose those functions that keep the inequality satisfied. So this is how this is parameterized. There's a bunch of parameters that also come in the weights of the quadratic objective function that you create. So, you know, exactly how do you weigh, for example, the control part versus the state part in standard linear quadratic regulators, for example? Well, as it turns out, and that was a bit of a surprise to me, the choice of these parameters actually matters. And then there's one more parameter, which comes from the soft constraints. And you have this whole parameter vector that basically the function of this reinforcement learning architecture is to learn those parameters. So let me return now to the merging problem, now that I've given you the way that we can handle this problem. And this is a real implementation of the CBF-based method in a merging problem, which is actually in the Boston area. I actually take this merging loop here every evening when I go home. And here you can see on the left, what happens with just human vehicles. This is just a straight simulation from standard car following models. And compare it to what happens when you have calves that communicate with each other. The important thing to notice is that the queue is being formed here because, as we know from experience, when you come from the on-ramp here, you typically slow down because you're at slower speed and merge only when you can and when you're allowed by the fast-moving highway. This is the Massachusetts Turnpike. For those of you who haven't been to Boston, main artery goes all the way from Boston actually to Seattle. And this is what happens when you apply this connected autonomous vehicle cooperative control algorithms. You can see that because these vehicles cooperate with each other, sometimes you can see them slow down or speed up, and there's never any congestion. Whereas here, eventually you create this type of backup, which is pretty serious. And this is not, fake. I've experienced this. So this works. And these are some numerical results that give you a sense of how close you can get to the true optimal control solution when you can get it, with or without noise. And this is just a sample. You can see you can get pretty close. So this optimal control with CBF constraints approach works quite well. Okay, so this comes to the last part of my talk, which has to do with this problem.
Suppose in the merging problem, this is no longer a cab, it's an HDV, a human-driven vehicle. You come here, and you come here, and you ask yourself, if you're a computer that controls your car, should I trust this HDV to let me in? Because I can no longer cooperate with it. So this brings up this issue of what do you do when there's unpredictable human drivers in the mix, and how can you solve this problem? What we do know is that it's a problem worth solving, because the exercise that I took you through with the optimal safe merging and all that has shown us that we can enhance safety significantly. By the way, we know that 94% of all car accidents in the world are due to human error. So if I can cut down on half of them with automation, then I've done something. We know we can reduce congestion. We know we can also reduce energy consumption. But the question is, this is all nice and good, but what do you do when you have these human drivers in the system that you have to interact with? As far as I can tell, there are three ways you can deal with this problem. One is to focus on perception and learning to develop better HDV models. In other words, predict the behavior of human drivers by using very good computer vision algorithms and so on. This is not my area of expertise, but I cooperate and collaborate with some colleagues who are teaching me about how that works, and this is a worthwhile direction. This is another direction which says prioritize safety, and once you can guarantee safety, for example, using CBS, then worry about optimality. But here's an interesting thing that we have found while pursuing this, is that sometimes the optimal and safe controllers that you derive can be independent of the human driver. And I'll show you an example of that. So I don't give a damn about the human driver. I can force him or her to behave as is socially optimal. And that's great. And then the third way is incentive type mechanisms, what we call cooperation compliance control. Mechanisms through which you can incentivize the humans to do what you know is the best for everybody. I will focus on this, and I'll close my presentation by giving you a little bit of ideas about this, which is fairly recent work that I've been doing. So let me illustrate this idea of how do I make the human driver irrelevant with this example, which is a lane changing problem. So imagine that you have these two green cars, which are cabs that can cooperate, and this human driver here with whom you do not cooperate. Now, you can see that if you are in these positions, there are two possible policies you can adopt. One is merge ahead of the HDV, so squeeze in there, and the other is go ahead of the cab. Suppose that I can solve each one of these options, determine the optimal control and the corresponding cost, compare, and follow the one with a lower cost. The important thing to notice is that in case 2, the HDV becomes irrelevant. Because if I go and I get ahead of this green vehicle, chances are that what happens is I go pretty fast, he decelerates a little bit, he forces the red vehicle to decelerate as well, and the red vehicle doesn't have a chance. They have to decelerate, and so they become irrelevant. What we have shown is that if you look at the cost as a function of the distance between these two vehicles, it behaves monotonically. So this is the cost. This is just an example of the cost. It behaves monotonically. By the way, this is not linear. It's slightly non-linear, but it is monotonically increasing. And what that means is that there's a threshold, in this case right here, so that if you're below the threshold, in other words, if the distance between the HDV and the cab is pretty small, then it is optimal to go and merge ahead of the cab. But if the distance is pretty large, so imagine this distance is pretty large, then it's optimal to go here, which makes sense. The distance is so large, I can safely get ahead of the HDV and you won't bother me. So if you can determine this optimal threshold, okay, then you could determine what is optimal to do. And in case where this is optimal, you couldn't care less about the HDV. So that's nice to know. This is actually a an experiment that we did, which I need to explain to you what's going on here. This is a lane merging case. I'll try to run it a few times. The HDV here is driven by a real person. So this is done in a simulation, but we have one of those steering wheels, and it's in 2 dimensions. So we have somebody actually driving this red car. And again, this is the controllable vehicle, and the ellipse here shows the safe region. So it's important when this autonomous vehicle is trying to change lanes, not to not to have, for example, the uncontrollable slow car ahead of it or the HDV get into this ellipse, which again, if you see how it's done, it guarantees to do that. But this is the case where the HDV is concerned. So we had the driver be kind of a little old lady that basically says, oh, somebody's trying to pass me. I'll just slow down and let him pass. More interesting is what happens when the HDV is aggressive, which is the next slide I will show you. So take a look at what happens here. You'll notice that the HDV now not only is competing with me, but it actually hugs the lane. And, you know, it's trying to prevent the AV to get ahead of it. So the AV recognizes that and says, okay, the hell with you, I'll just slow down and get behind you. So, and this was done optimally, but using these CBF-based controllers. The important thing is this, that this guarantees safety. So here we sacrifice performance because obviously we had to slow down and get behind the aggressive HDV, but at least we're able to do it. This is a picture of what we're doing in our own laboratory. We have a robotics laboratory at Boston University. We bought a fleet of these robots that are called limos. They're made by a company called Agilex. If you're interested, they're about this big. They're not as small as we like them, but they're not too big. And we make them follow our algorithms and go through this merging scenario. We have different merging scenarios. And if you visit this link, you can see the actual videos. More exciting to me is something that we're doing now in another lab, where we're actually installing a video floor. So imagine your laboratory where the entire floor is a screen. This is sample. We have it ordered, and before we actually ordered it to be customized to our lab, they sent us this sample that you see here. And so you project on your floor the urban or suburban, whatever landscape that you want. So I don't have to build, you know, a hardwired little cars and not just cars, but houses and roundabouts or whatever. I can configure whatever landscape I want, but just clicking a button. It's just a screen. On top of the screen, we have the real robots moving, but in addition, you can see them here, we also have virtual cars. One that's faint over here. That allows me to have heavy traffic. I can have hundreds of these virtual vehicles running, and then a few, maybe 10 or 15, of the real vehicles that can interact with it. And this is a lot of fun because students love it. And you can actually, for example, treat these as the calves and these as the HDV. So these are uncontrollable and these are controllable and cooperative. So this is something that we're just starting. I just wanted to show it to you because it seems to me that this is the future in terms of laboratories. If you want to do this sort of laboratory test bed experiments, this is the way to go as opposed to build, you know, hardwired things which are difficult to move around and change. So let me close with a few thoughts on cooperation and compliance. So I showed you before a scenario in which I had two calves that were cooperating and one HDV that I could actually force to do what I want in some cases. What if I have two HDVs here and I really need to change lanes because I'm slowed down by this uncontrollable vehicle ahead of me? How can I convince these two guys to let me get there? So these are the fundamental questions. Why should these two vehicles, you know, cooperate with me? And in particular, you see that for this to work, most likely, this guy has to decelerate to let me go in. This guy may have to accelerate, but in any case, focus on this guy. Why should I decelerate? Why should I, you know, get away from my comfort zone just to let you get ahead of me? This is the fundamental question. So what we are experimenting with that seems to work is what we call a refundable toll concept. Every driver, if they want to participate, is given a digital wallet. We're all familiar with that concept. And we borrowed, actually, this is something that we didn't really invent, so I give credit to these papers, in particular this one that sort of proposed the same. Then the user, the driver that starts their commute on a typical day, commits a number of tokens at the start of the trip as if it was a toll. So instead of going through a physical toll booth, you simply commit, whatever it is, $100, $10 for the rest of your daily commute. But the important thing is that the toll is fully refundable as long as the user complies with a set of rules. So there are the rules of the road, and as long as you comply with them, for example, let me get ahead of you, right? If you comply with this rule, throughout the day, you get all the money. The other important thing is that the tokens are virtual. It can only be used within a given market. You don't want to have real money, get into the game here and start people essentially hacking the system. So the first time that we tried that, we found that it was very easy to hack the system. You just go in there with your digital wallet and you would accumulate a lot of tokens by being nice. And then, eventually you just collect a lot of real money and disappear. All right, so how does this work? In this case, what I want to consider as a rule is this rule. Accommodate lane changing from a vehicle in the slow lane when a request is received to me. So I'm in the fast lane and I'm being asked to let a guy get ahead of me, which probably means that I need to decelerate a little bit, or at least not accelerate. Just let him get ahead. So there is a variable, which is a random variable, typically, m sub I k. K indicates time steps, which is selected to be inversely proportional to the deviation of the actual state of the agent, I in this case, from a desired reference. And we have a concept of a social planner, which is a centralized authority that actually has determined the socially optimal solution to a problem. It could be a routing problem, or it could be individual lane changing maneuvers. The simplest possible case is to treat this as a random variable that takes values 0 and 1. 0 means that you're not complying with the request, 1 means that you're complying. And then the whole goal is to maximize the compliance rate, this compliance probability. And ideally you want to get it to 1, but maybe 95% is good enough. So the architecture is this. You have the social planner in here. Social planner interacts with a subset of your system, which are the CAVs, typically, the compliant agents. And then there's these other agents which are non-compliant. These are the guys that I want to incentivize. But these guys help me because they provide information. For instance, through this link here, they can provide information about the behavior of the non-compliant agents, which I can then take into account in order to do some control here. What is this control? The control is based on some virtual costs. And the important thing is to notice that there are 2 components to this cost. One is a cost, a token, part of this toll, which every user contributes towards the global optimality. So everybody pays that. This is the price to pay for all of us to achieve social optimality. And then you have an individual component, which essentially penalizes those who are non-compliant more than those who are compliant. So this is to accommodate the fact that some people are nicer than others. So for the people who are not nice, they're going to experience a higher cost. How does this cost work? Well, it's a very simple feedback mechanism. This is like control theory 101. And you simply have an iterative scheme over time k, which adjusts this cost and hopefully converges. And the goal is to achieve a desired compliance rate, Q star, and these are just simply parameters to be tuned. So it's a very, very simple scheme. And the compliance probability, which needs to be updated, has to take a form which intuitively must be monotonic in certainly the innate characteristic of user I, how altruistic or selfish they are, and then components which are functions of these costs. that I can control. And the question is, what is the form of this compliance probability function? We use this very simple form for now, but the important thing is that it needs to be learned. So this is another opportunity for some learning methods to learn the right compliance probability to use. I'm just going to show you and close my talk with just some early results that we have in the scheme for the lane changing maneuver. So in the lane changing maneuver, the social planner has determined a trajectory, which is the reference trajectory. And this is what the user actually does. And that's the norm of the deviation from the reference. And we evaluate that through a compliance probability, that's not probability, compliance measure, which takes values between 0 and 1. So 0 means that the agent is totally non-compliant. So 0, yeah, I don't comply, I ignore it. Otherwise, the compliance is measured on a relative basis depending on the error that is defined by this difference. Okay, so the bigger the error until it reaches the maximum value, the more non-compliant you are. If you're perfectly compliant, then this gives you a 1. So in this particular example scenario, you see that we have a mixture of CAVs and HDVs. The important HDVs here are these two, because this is the target vehicle, the ego vehicle that wants to merge. This actually doesn't matter so much because he's ahead, so what he does doesn't really matter. This is the guy that really must comply to allow this vehicle to merge here or here. You know, this is the guy that will target. And these are some results that show you that this simple scheme actually converges. In fact, it can converge to a compliance rate of 1 within reasonable time. And these are the values of the global cost component and the local cost component. They also converge. The physical significance of what they converge to, I'm not sure I understand yet, but it's got to have some meaning. But the important thing is that these mechanisms converges. And this is just to show you a notion of fairness. This is not very well illustrated with just a couple of HDVs, but if I had more, you would see that the vehicles that are least compliant are the ones that get a bigger local cost component. The global cost everybody pays, but it's very clear that you need both. That's really the important message here. And I'll just close by just leaving you with a few of the questions that I consider open and interesting in this whole autonomous multi-agent environment, particularly when it comes to transportation systems. A key question is, what fraction of autonomous vehicles do I need to realize the definite benefits? 2%, 5%, 10%, 90%. I think this remains open. We've done a lot of empirical studies of that. Our general conclusion is that typically it doesn't take that many to realize benefits, maybe 10% rule of thumb. But it remains an open question. It probably depends on the case. How do we integrate CAVs with pedestrians, bicycles, and so on? So this is a question that I get all the time. For example, officials from the city of Boston, which wants to pride itself on being very bicycle friendly now, and of course, lots of pedestrians. How do you integrate that? That remains an open question. There are ways to do that, but you know, it's an interesting question. How do we incentivize compliance for social optimality? I've already given you some thoughts on that using this cooperation compliance control, but I think this is an interesting question. Is shared mobility on demand the long-term answer? If you look at the statistic that we all use our cars for an average of 4%, our cars are a terrible investment. I mean, you buy this expensive cars sometimes if you want to show off, and you use it 4% of the time. The rest of the time it just stays parked. So maybe the solution is that we should migrate to a mobility, shared mobility on demand system, and therefore some research should be done on these types of systems, the so-called TNC, Transportation Network Control, can't remember. Anyway, Uber and Lyft. How do you control these and manage systems of this type? What is the role of learning in the more general context of multi-agent systems, autonomous multi-agent systems, which need to guarantee safety? Can you learn optimal trajectories online safely? I showed you that it can be done because if you replace the hard constraints with CBFs, these problems become manageable, tractable, and the training that you would do in whatever your favorite machine learning algorithm is can be safe. And I think that's important. And I'll leave you with these thoughts, and thank you very much.
Are there any questions? Some questions?
Thank you for the presentation. So, can you elaborate more on the role of the social planners that you mentioned in the last part of your?
Yeah, but you won't like my answer. I don't know exactly what that entity would be in practice. So for the time being, we consider it as a kind of a central authority, an abstract notion of a central controller who does everything. Exactly how that might be implemented in the real world, I don't know yet. But I don't think it would be that weird a concept. I mean, there are offices, central control offices in all the big cities and in all the regions that do that control things. If you empower them with algorithms that can dictate how the traffic should behave and give recommendations, at least to the vehicles, then that would be the role of that social plan. But the important thing, and that's why we call it social, is that it comes up with socially optimal trajectories or solutions like routing. We're trying to do that on a routing problem. That's all I can really say.
Hi, Christos. I must admit, last time I had to give a presentation a couple of years ago, the same topic. You made big jumps.
Oh, yeah. This is
Yeah.
yeah.
So, let me go back to this question of the control value. Now, I mean, if I recall, you have constraint, which is the point-wise constraint. You had some safety point-wise constraint in the state. Wouldn't you be able to handle this if you looked at your optimization problem from the point of view of the dynamic programming equation, instead of contracting maximum principle? Because there will be a point-wise constraint, and then you can bring in reinforcement learning to be able to get a feedback solution. Because you know.
Yeah. So
And of course, you avoid the issues of smoothness, differentiability with the
Lipschitz, you need Lipschitz continuity for all this to work. Yeah. So the starting point does not involve dynamic programming or contracting. It's not an optimization scheme. I have some constraints which I want my controller to satisfy. I want to come up with feedback control laws that guarantee those constraints, no optimization. Then I add the optimization part and I say, okay, then what I should be doing once I know that I can guarantee these constraints is do it in some optimal fashion, not just feasible, but optimal. That's where I formulate the optimization problem. Whether I formulate it as a dynamic program or as just Hamiltonian type, like Pontryagin type, I think that's up to you to decide how to do it. There is a framework to do it, as I described, which essentially replaces the original hard optimization problem constraints by constraints which are linear in the control. And that's the benefit. How you do the optimization is more or less up to you. For example, we do MPC, model predictive control, which is an optimization technique And that's the choice that we make there. But the crucial first step is to replace those point-wise, as you said, constraints by these inequality constraints that tell you what is the control that guarantees them, and these may be conservative. That's
Yeah, that was kind of my second question. Basically, what you wanted to do is you gave more emphasis on my understanding. You gave more emphasis on finding the control at the beginning with the barrier function. And then the optimization
Comes after.
Like restricted around that.
yes,
Strategy.
yes. And the reinforcement learning, for example, component that we brought in allows you to create some flexibility on how to tune some parameters to manage the trade-off between conservativeness and performance. If you want to put it in a broader control theoretic context, it's really a third dimension in how control theory could view itself. So far, all of control theory is based on a trade-off between performance and computational complexity. Okay, I mean, basically, you have to determine this sophisticated controllers when they become computational too complex, you give up and you trade off. This is a third dimension, the safety or conservativeness, because again, I have to deal with computational complexity. If I choose those class K functions to be nonlinear and very fancy, start becoming computationally pretty complex. Most people use linear functions, and we do most of the time, just linear constraints instead of nonlinear barrier functions that are intuitively probably more able to capture the trade. But that's what we are. We create a new context for you to decide what it is worth trading off.
Thank you.
Other questions? Christos, how, is there another one? No. How robust is it, or is it, I mean, because you have some leeway, so there's going to be disturbances, the models, some cars will be bigger, some, and also how tolerant, I mean, that's the other thing is, some of the sensors or some of the actuators don't work as expected, so is it, with autonomous cars, is this one of the issues that there might be some concern about?
Yeah, three answers. One, empirically, when we inject noise, and I showed some tables, just noise, measurement across noise, it seems to work well. Two, Christos yesterday asked me the same question. In the control barrier function theory, what you do is you look at the worst case. And so typically you say, yes, there could be disturbances, but I'll consider a finite support of my probability distribution that characterizes those disturbances. And then you create what are called robust control barrier functions, so that you can make sure you become even more conservative. Okay. So the conservativeness enforces the safety, even in the presence of these disturbances that you have bound. The event-driven techniques essentially treat those bounds as events. So if you have a disturbance and it increases, at some point you say, okay, this is the maximum disturbance that I can tolerate, and that becomes an event, you update, and you hope that you can compensate for it. The third answer that I will give you is something which people have started looking into, which is create a stochastic extension of control barrier functions. Sometimes, we call them chance constraints, as opposed to hard deterministic constraints. And so now you replace the certainty of the safety guarantee with a probabilistic measure. I have not personally looked too much into that, because for the autonomous vehicle type of applications, the disturbances, like the sensors that you say, are fairly easy to detect. I mean, if suddenly I see a vehicle which says, the camera doesn't work anymore, and I can't predict anything, you can do something about that and you can handle it. But in theory, this is an important question. And so the chance constraint, the stochastic extension might be the way to go. There was a question in the back there. Something.
That's very interesting work. I was wondering, very interesting work, focused mainly on microscopic, in a microscopic framework, let's say. How do you see how do these ideas expand on a macroscopic framework, and how the microscopic, let's say, local improvements, let's say, on some junctions, can affect the macroscopic behavior. And this actually connects with the social planning.
Yeah. That's an interesting question. So a lot of people in robotics use control area functions type of techniques. At the microscopic level would be the typical robotic navigation. I want to avoid some obstacles and so on. But some people have looked at swarms of robots moving around, in which case you have to elevate the level, as you say, from micro to macro, and consider flows. Let's say. In transportation, that's the flow level, macro level, in which case you can consider, for example, routing problems as flows. There are standard elegant optimization problem formulations. You can create similar type of control barrier functions for these types of problems, or you can try to solve the macro problem to give you a reference, similar to what I was saying. Let's solve an unconstrained problem, and then try to get as close as we can to the unconstrained solution, but guaranteeing that we stay safe. So maybe you can use your macro level to come up with a flow level solution, use that as a reference, and then say, how can I get as close as possible with my individual car? That's the best. We are actually looking at this in the context of a routing problem, where the higher level is, let's find a flow solution which is optimal, has some properties, and then try to use these techniques to ensure that you can get as close to the flow socially optimal solution at an individual agent level.
Say their Lipschitz continuity of the solution to the current problem. They necessity the answer is that if we really want to sort of get forward to consider the option to do that the option. So that in this case, the code is already discontinuous dynamics. So I would so we can to
Is your question whether we need it, or is the question how do I guarantee that I have Lipschitz continuity? Yeah. Okay. So actually, I had the same question a few years back when I started looking into this CBS, and my best answer is based on my intuition. If you are a robot that navigates around and you suddenly see an obstacle, but it's too late. You see it too late. Your sensor just doesn't have enough of a range. You're moving pretty fast. That's important. So I move really fast and suddenly I see an obstacle. Yes, I could stop by decelerating hard, but this is where the Lipschitz continuity comes in. I cannot decelerate instantaneously. I have to have the ability to decelerate over some finite interval of time. Mathematically, the whole basis of the CBF theory is based on a theorem, which is called Nagumo's theorem, that dates back to the 40s. And if you look at that initial theorem statement, you will understand, I think, mathematically, why you need this assumption of Lipschitz continuity. Practically, it's what I said. I just cannot go and apply my control from 0 to infinity. For example, I can't go from zero deceleration to infinite deceleration to stop. I need a little bit of time. That's where these class K functions are there for, to create this safety margin, if you will, to allow you to satisfy that inequality within practical constraints.
Any last question? Thank you, Christopher. Be with us until next Friday, not tomorrow, the Friday after. So you have to publish
Yeah, be very interested in seeing your problems, your research projects, and how we can perhaps collaborate in terms of mixing what you do with some of these ideas, whether it's reinforcement learning, MPC, CBFs. I think there's a lot of interesting problems there.